In this video, we are going to study Cauchy's homogeneous linear differential equations such as x square d2y upon dx square minus 2x dy by dx plus 3y equals x, which is a function of x. Here we observe that the coefficients of the differentials are not constants but are powers of x of a particular type. These equations, by proper substitution, can be easily converted into linear differential equations with constant coefficients. For example, this Cauchy's equation x square d2y upon dx square minus 3x dy by dx plus 4y equals 2x square by certain substitutions such as z equals log x, or in other words x equals e raised to z, can be converted into a linear differential equation with constant coefficients d2y upon dx square minus 4 dy by dx plus 4y equals 2 e raised to 2z, where the coefficients of the differential are constants. The complete solution in the form of complementary function and particular integral can be found out by usual methods, about which we have discussed in detail in my previous videos on linear differential equations with constant coefficients, whose links have been provided in the description box. So in this video, we are specially going to focus on transforming Cauchy's homogeneous linear differential equations into linear differential equations with constant coefficients only. Hello friends, you are watching YouTube channel Number Collage. This channel features videos on mathematical concepts. Effort has been made to explore the concepts through basic mathematical ideas. Hope you will like my effort. In this video, we are going to study Cauchy's homogeneous linear differential equations. Differential equations of the type x square d2y by dx square plus x dy by dx minus y equals 8x cube, or x cube d cube y by dx cube minus x square d2y by dx square plus 2x dy by dx minus 2y equals x cube plus 3x are called Cauchy's homogeneous linear differential equations, where coefficients of differentials x square, x cube minus x square, 2x etc. are in descending powers of x, and their right hand side is a function of x such as 8x cube or x cube plus 3x. By suitable substitutions, Cauchy's equations can be transformed into linear differential equations with constant coefficients, which can be solved by usual methods, about which we have discussed in my previous videos, the links of which have been provided in the description box. In this video, we are specially going to focus on this transformation of Cauchy's equations into linear differential equations with constant coefficients. By special substitution, z equals log x, which also means x equals e raised to z, and further processing on it, this Cauchy's equation getting transformed into d2y upon dx square minus y equals 8 e raised to z, and this Cauchy's equation getting transformed into d cube y upon dx cube minus 4 d2y by dx square plus 5 dy by dx minus 2 equals e raised to 3z plus 3 e raised to z. We find that the coefficient of this d2y by dx square, which is x square, has been transformed into a constant 1, and the function on the right hand side 8x cube has been transformed into 8 e raised to z. Coefficient of this d cube y upon dx cube, which is x cube, has been transformed into a constant 1 here. Coefficient of this d2y by dx square, which is minus x square here, has been transformed into a constant minus 4, and the coefficient of this dy by dx, which is 2x has been transformed into a constant 5 here, and here the right hand side x cube plus 3x has been transformed into e raised to 3z plus 3 e raised to z. Now these two equations, being linear differential equations with constant coefficients, can be solved by usual methods. Now we will see how this special substitution z equals log x can be used for this required transformation. So differentiating this with respect to x, we get dz by dx equals 1 upon x, but we want dy by dx, which by chain rule will be dy by dz into dz by dx. But dz by dx is nothing but 1 upon x. So therefore dy by dx will be 1 upon x into this dy by dz. We name this 1 and rewrite 1 as x dy by dx equals dy by dz. We name this 2. Next, we will differentiate equation 1 with respect to x, which will be derivative of dy by dx d2y upon dx square equals, for differentiating 1 upon x into dy by dz, we have to use product rule of differentiation. So first function into derivative of second d2y upon dz square. Now since we are differentiating with respect to z, so we have to multiply this by dz by dx plus second function, which is dy by dz into derivative of first function 1 upon x, which is minus 1 upon x square, which is 1 upon x into d2y upon dz square into, we have dz by dx equals 1 upon x, so into 1 upon x minus 1 upon x square dy by dz. This will be d2y upon dx square equals 1 upon x square d2y upon dz square minus 1 upon x square into dy by dz, which will be 1 upon x square d2y upon dz square minus dy by dz. We name this 3 and rewrite it as x square into d2y upon dx square equals d2y upon dz square minus dy by dz. We name this 4. So far we have found two results. One is x dy by dx equals dy by dz. Number 1, x square d2y upon dx square equals d2y upon dz square minus dy by dz. Number 2, and now we will differentiate this equation to find the third result. So differentiating with respect to x, we get d cube y upon dx cube. We will use product rule here, 1 upon x square. First function into derivative of second d cube y upon dz cube. Since we have to differentiate with respect to x, we will multiply here by dz by dx plus second function d2y upon dz square into derivative of 1 upon x square minus 2 upon x cube minus, using product rule here also, 1 upon x square into derivative of dy by dz d2y upon dz square. But since it is with respect to x, we multiply here by dz by dx plus second function dy by dz into derivative of first function 1 upon x square, it will be minus 2 upon x cube. Now here for dz by dx we have this 1 upon x, and for this dz by dx we have 1 upon x. So this will be 1 upon x into 1 upon x, 1 upon x cube d cube y upon dz cube minus 2 upon x cube d2y upon dz square minus 1 upon x square into 1 upon x, 1 upon x cube d2y upon dz square plus 2 upon x cube dy by dz. This further will be d cube y upon dx cube equals, taking 1 upon x cube as a common factor, into this d cube y upon dz cube minus 2 minus 1 minus 3 into this d2y upon dz square plus this 2 dy by dz. And this equation gives us third result, which is this x cube into d cube y upon dx cube equals d cube y upon dz cube minus 3 d2y upon dz square plus 2 dy by dz. We name this number 3 by using d equals d by dz. Same results can be written as x dy by dx equals dy by dz equals dy. Second result can be written as x square d2y upon dx square equals d square y for this d2y upon dz square minus dy for this dy by dz. Third result will be x cube d cube y upon dx cube equals d cube y for this d cube y upon dz cube minus 3 d square y for this d2y upon dz square plus 2 dy for this 2 dy by dz. This second result further will be d into d minus 1 y, and the third result further will be d into d square minus 3d plus 2y, which further will be d into factors of d square minus 3d plus 2 d minus 1 into d minus 2 into y. So when the coefficient of dy by dx is x, we use dy. When the coefficient of d2y upon dx square is x square, we use d into d minus 1 into y. And when the coefficient of d cube y upon dx cube is x cube, we will use d into d minus 1 into d minus 2 into y. Solve x square d2y upon dx square minus 3x dy by dx plus 4y equals 2x square. This is Cauchy's equation because the coefficients of differentials x square and minus 3x are in descending powers of x. We can convert Cauchy's equation into linear differential equation with constant coefficients by substituting z equals log x, which also means x equals e raised to z. Now, according to what we have written here on the wall, we will substitute for this x square d2y upon dx square d into d minus 1 minus 3 for this x dy by dx d plus 4 y equals 2 for this x square e raised to 2z, which will be d square minus d minus 3d minus 4d plus 4 into y equals e raised to 2z. Now putting for this d by dz, it will be d2y upon dz square minus 4 dy by dz plus 4 y equals 2 e raised to 2z. We find that original equation was in terms of y and x, but the new equation is in the form of y and z, which is linear differential equation with constant coefficients, because here the coefficients of the differential are constants, 1 here minus 4 here, instead of x square minus 3x in descending powers of x as in Cauchy's equation. Now this linear differential equation with constant coefficients can be solved by usual methods. Now we have this linear differential equation with constant coefficients, which will be d minus 2 whole square y equals 2 e raised to 2z. Here auxiliary equation is d minus 2 whole square equals 0. That gives two equal roots 2 and 2. So complementary function will be for repeated roots c1 plus c2z into e raised to 2z. In terms of x, cf will be c1 plus c2 log x and e raised to 2z will be x square. We name this 1. Particular integral will be 1 upon d minus 2 whole square operating on 2 e raised to 2z, which is this 2 into, if we put this d equals this 2, the denominator will be 0. So we write this z upon derivative of d minus 2 whole square, which is 2 times d minus 2 e raised to 2z, which is cancelling this 2. If we again put this d equals this 2, the denominator will be 0. So we write z square upon derivative of d minus 2, which is 1, into e raised to 2z. So particular integral in terms of x will be, for z square we write from here log x whole square, and for e raised to 2z from here x square. So x square into log x whole square. We name this 2. Now finally we write the complete solution, which is composed of complementary function cf and particular integral pi, which will be c1 plus c2 log x into x square plus particular integral x square log x whole square. Solve x square d2y by dx square minus 3x dy by dx plus 5y equals sin log x. This is Cauchy's equation because the coefficients of the differentials are in descending powers of x square and minus 3x. To convert this into a linear differential equation with constant coefficients, we substitute z equals log x, which means x equals e raised to z. This allows us to substitute for this x square d2y by dx square, this d into d minus 1 minus 3, for this x dy by dx, this d plus 5y equals sin z. This will be d square minus d minus 3d minus 4d plus 5y equals sin z. In terms of differentials, this will be d2y upon dz square minus 4 dy upon dz plus 5y equals sin z. Here the coefficients of differentials are constants, 1 here in place of x square, minus 4 here in place of minus 3x, etc. This is a linear differential equation with constant coefficients which can be solved by usual methods. From this equation we get auxiliary equation t square minus 4d plus 5 equals 0. This is a quadratic equation, and after solving we get the root d as 2 plus minus I. So complementary function accordingly will be y equals e raised to this 2z into c1 cos z plus c2 sin z. In terms of x, this will be y equals e raised to 2z will be according to this x square into c1 cos z will be according to this cos log x plus c2 sin log x. We name this 1. Now particular integral will be 1 upon d square minus 4d plus 5 into this sin z. This will be 1 upon, when there is sine function here, in place of d square we substitute minus square of this 1. So this will be minus 1 square minus 4d plus 5 sin z, which is 1 upon minus 4d plus 4 sin z minus 1 upon 4 into 1 upon d minus 1 sin z. Whenever there is sine, we must have d square in the denominator. So we bring d square by writing this as minus 1 upon 4. We multiply numerator and denominator by d plus 1. Upon this will be d square minus 1 sin z. Particular integral further will be minus 1 upon 4 into d plus 1 upon, when sine function is here, we substitute in place of this d square square of this minus 1. So it will be minus 1 square minus 1 sin z, which is minus 1 upon 4 into minus 2 1 upon 8, and d plus 1 into sin z will be sin z plus d sin z. So finally particular integral will be 1 upon 8 into sine of, in place of z we write from this log x plus derivative of sin z is cos z, so it will be cos, and in place of z from this we write log x. We name this 2. Now from this 1 and from this 2 we write complete solution of Cauchy's equation as y equals c1 cos log x plus c2 sin log x plus this particular integral 1 upon 8 sin log x plus cos log x. Solve x cube d cube y upon dx cube minus x square d2y upon dx square plus 2x dy by dx minus 2y equals x cube plus 3x. This is a Cauchy's equation which can be transformed into linear differential equation with constant coefficients by substituting z equals log x, which means x equals e raised to z. This substitution allows us to use for this x cube d cube y upon dx cube this d into d minus 1 into d minus 2 minus for this x square d2y upon dx square from this d into d minus 1 plus 2 for this x dy by dx from this d minus 2 into y equals x cube from this will be e raised to 3z plus 3x will be 3 e raised to z. After simplification, this will be d cube minus 4d square plus 5d minus 2y equals e raised to 3z plus 3 e raised to z. This is linear differential equation with constant coefficients which can be routinely solved to find complementary function y equals c1 plus c2 log x into x plus c3 x square and particular integral equals x cube upon 4 minus 3x upon 2 log x whole square. Therefore, complete solution of Cauchy's equation will be y equals this complementary function plus this particular integral. If you like this video, please like, share and subscribe this channel. See you in the next video. Until then, keep watching Number Collage. Thank you.